In this pre-calculus algebra video, we will solve a system of linear equations given three variables. We will verify whether an ordered triplet is a solution to a given linear equation system, and we'll also solve an application problem using a system with three variables. When we had a system of equations with two variables, an ordered pair solution, we needed three equations in that system in order to solve for the two variables. If we have three variables, an x, y, and a z, for example, the solution set is going to be an ordered triplet, an x, y, z, but in order to solve that system of equations, we're going to need three equations. The number of variables needs to match the number of equations in a system in order to be able to solve it. Here's an example, and we're given an ordered triplet, and we're asked, does this ordered triplet solve the system? So when x is 2, y is, let me write this out for us. When x is 2 and y is -1 and z is 3, do those three variables satisfy all three equations? Notice, by the way, as we do this unit, there's a lot of writing, a lot of x's, y's, z's. Notice how I'm writing my x's and y's. I'm writing them with a little bit of curl to them, a little cursive V. I'm writing the z with a slash through it. Here's why. If I write my x or my y really quickly, it's harder and harder as I I'm trying to do it fast. As I write those y's, it's harder and harder to differentiate. Wait, is this an x or is it a y? Right, so by making that x a little bit curvy and making that y more like a cursive y, it makes it very easy to distinguish an x from a y. And by drawing a line through the z, makes it easier to distinguish that that is a z, not a 2. Here's how we'd go about checking whether a ordered triplet is a solution to the system. We're going to plug in a 2 for x, a -1 for y, and a 3 for z, and see if we get a true statement. That's why we've got this question mark above the equal sign. We're not sure whether it's equal or not, but we'd have 2 minus 1 plus 3, and we're checking, does that equal 4? When we add those, we'd get 5 minus 1, which is 4. So it looks like, yes, our ordered triplet does solve the first equation. Let's check the second equation. X minus 2y minus z equals 1. And we want to check if x is 2 and y is -1 and z is 3, do we get a 1? So we've got a 2 plus 2, because a -2 times a -1 is +2, minus 3, that gives us 4 minus 3, which is 1. So it looks like our second equation can be solved with that ordered triplet. Let's try the third equation. 2x minus y minus z equals -1. When x is 2 and y is -1 and z is 3, we'd have 4 minus -1 would be +1 minus 3, that's 5 minus 3, which is 2, and it looks like we don't have a consistent statement because 2 does not equal -1. I could go back to check this to make sure I didn't make a mistake. 2x is 4, minus -1 is +1, so that's 5, minus z minus 3, so 5 minus 3 is 2, and yeah, it looks like we did do it correctly, and our ordered triplet is not a solution to the system. It's not a solution to the system. It was a solution to the first two equations, but not to all three, so we'd say it's not a solution to the system. Let's look at another example, and in this example, we're going to actually solve to find the solution. Now I've done some of the work here to speed the the video along, but I'm going to walk through, explain each of these steps that I took. First of all, I numbered each equation, equation number 1, equation number 2, and equation number 3. That's a great way to start every time. It's also a great way to start by writing each equation carefully and even double check that you've written each equation carefully. 4x minus y plus 2z equals 11. And then the next step is, after I've written the system carefully and numbered each equation, I want to look to see which variable might be easy to eliminate. As I looked at this example, it looked to me like the y variable might be the easiest one to eliminate because we have a negative y, and then we have two of them that already match up, a 2y and a 2y. So that is why I'm going to choose to eliminate y. I'm going to eliminate y in the 3 equations so that I could eventually have just 2 equations. Here's how I'm going to do that. I could look at equation 1 and see that the opposite of y and positive 2y, if I multiplied equation 1 times a factor of 2, I would have a negative 2y, and when I add that negative 2y to 2y, I'd be able to eliminate it. I'd be able to eliminate the y. So let's do that, and I'm going to note it with this notation here, 2 times equation 1, and that's going to equal 2 times 4x is 8x, 2 times the negative y is negative 2y, 2 times 2z is 4z, 2 times 11 is 22. So I have an 8x minus 2y plus 4z equals 22. Now I'm going to call that the new equation 4. If I take my new equation 4 and add that to equation 2, I'd have 8x minus 2y plus 4z equal to 22 plus x plus 2y minus z equals negative 1. When I add those, I'm going to get 8x plus x is 9x. The y's cancel out, 2y minus 2y. 4z minus z is minus 3z. 22 minus 11, so we have it equal to 21. So that's going to be our new equation 5. I've eliminated the y using equation 1 and 2. The next step is to eliminate y using equation 3 because I haven't used it yet. And I could use my new equation 4 or my equation 1 or my equation 2. But one of those 3 will need to be combined with equation 3 to solve or to eliminate y. When I look at the equations, I can see that both the equation 2 and equation 3 have a factor of 2, have a coefficient of 2 in front of the y. So I could subtract those equations from each other, take equation 2 and subtract equation 3, for example, to eliminate the y's, and that's what I'm going to go ahead and do. Now, subtraction is sometimes difficult to keep track of, so I'm going to change the subtracting to adding. I'm going to change it to adding the opposite. So with a different colored pen, I'm going to change the subtracting to add, and I'm going to go in and distribute that negative to all 4 pieces. The 2x, 2y, the negative 3z, I can make it positive with 1 mark, and the negative 1 can become positive with 1 mark. And now I'm going to add the 2 equations. So add equation 2 to the opposite of equation 3. So x minus 2x is negative x. 2y minus 2y cancel each other out. 3z minus z is 2z. Negative 1 plus 1 is 0. So it looks like my second equation is negative x, or the opposite of x, plus 2z is equal to 0. And then we already had, so that's our equation 6. And we already had our equation 5. 9x plus 3z minus equals 21. Let's talk through for just a minute, looking back what we did. We used all three equations to eliminate y, and we were sure that we used equation 1 and 2, and then we have to use equation 3 and any of the others. I chose 2. But as long as we've used all three equations and we've eliminated one of the variables, we're ready to move forward. Now it's like a system of equations from a previous example, from a previous section, where what we had was where we're just starting with two equations. I'm going to erase some of this, or actually, I'll leave it here. I was going to erase this piece to the left, but we'll leave it there for now. But we might need to go back to erase it to make more space. Well, let's see. If I take equation 6 and solve it for x, I'd have x equals 2z. And then I could use substitution to substitute 2z in for x in equation 1. So equation 1, 9x plus 3z equals 21 would become 9 times 2z plus 3z equals 21. So 18z plus 3z equals 21, or in other words, 21z equals 21, divide by 21, and we get that z is equal to 1. There's our first variable solved for. We have z equals to negative 1. We're going to now use back substitution to find x and y. Look at equation 6. Do you see that equation 6 is going to be an easy equation to use to solve for x? Because if we have x equals 2z, then all I have to do is put in a 1 for z, and I'd have x equals 2 times 1, or x equals 2. So now we have z is 1, x is 2. We just need to solve for y. I can go to any of our original equations or even our equation number 4. Best usually to just go to an original equation. And if I'm solving for y, I could pick any of those. I'm going to go ahead and pick the number 1. The reason I'm going to pick number 1 is I could add y to both sides and just have that y equals, if I add y to both sides, I'd have y equals 4x plus 2z minus 11. So subtract 11, so take the y and move it to the right, the 11, move it to the left. So I'd add y and subtract 11, and I'd have y equals 4x plus 2z minus 11. Substitute in 2 for x and 1 for z. 4 times 2 plus 2 times 1 minus 11 would give us 8 plus 2 minus 11. That's 10 minus 11, or let me make sure I've got that. So that y is equal to negative 1. It doesn't hurt to stop and check as you go. Look back over your work, make sure you haven't made a small mistake here or there. But it looks like our answer is, let me erase this part on the right now. We've got this. Looks like our solution is x equals 2, y equals negative 1, z equals 1. And how do we check that? How do we verify that? So we've got the ordered triplet x, y, z. And if we want to check it, we could go into each equation and replace. So 4 times 2 minus negative 1 is plus 1, plus 2 times 1, 8, 9, 10, 11 equals 11. So it looks like that does solve our first equation. For our second equation, x plus 2 times negative 1 is negative 2, minus z would be negative 1, and that does equal negative 1. So our second equation checks out. And then for the third equation, equation 3, our original 3, 2 times x plus 2 times y minus 3 times z, 4 minus 2, 4 minus 2, minus 3. Sorry, this pen is really going crazy here. Let me erase that and try it again. I think I'm going to have to write a little more slowly because the pen is having a hard time keeping up. So we'd have 2 times 2 is 4, minus 2, minus 3. So 4 minus 5, negative 1. So it looks like it checks out for the third equation. So our solution is x equals 2, y equals negative 1, z equals 1. Let's move on to a new example. And by the way, let me just add in here. The best way to get good at these is to actually jump in and practice. You can't get good at solving a system of 3 equations, 3 unknowns, unless you actually jump in and try these different examples. You've got to try it yourself and develop your own pattern for how to solve these types of problems. Number 3 is an interesting application problem. Find the quadratic function y equals ax squared plus bx plus c such that the graph of that parabola passes through the points 1, 6, x equals 1, y equals 6, 1, 4, so x equals 1, y equals 4, and 2, 9, the ordered pair x equals 2, y equals 9. The first step in finding this quadratic function is to get the system of 3 equations. So I'm going to take each of the 3 points. So here's the 1, 6, and I'm going to replace x with negative 1, y with 6, and I'd have 6 equals a times negative 1 squared plus b times negative 1 plus c, and that'll give me the equation 6 equals a minus b plus c. If I replace x with 1 and y with 4, I'd have 4 equals a plus b plus c. And then in the third equation, replace x with 2, y with 9. We'd have 9 equals 2 squared, or 4, times a, plus 2b plus c. So it looks like we have a system now of 1, 2, 3 equations. We can solve that system of 3 equations for a, b, and c. And when we solve that system of equations for a, b, and c, we'll be able to plug those back into the y equals ax squared plus bx plus c. Let's walk through how to go about doing that. Let me see if I can get the page to move just slightly. There we go. So our equation 1, number each of these equations. We've got our equation 1, a minus b plus c equals 6, and our equation 2, a plus b plus c equals 4. It'd be easy to eliminate b by adding those. So I'm going to add equation 1 to equation 2 to get 2a plus 2c equals 10. And that's now our new equation 4. I need to now eliminate b using equation 3. I'm going to use 3 times a factor of negative 2 times the first equation. So negative 2, or not first, the second equation. Negative 2 times equation 2, a plus b plus c equals 4, added to 4a plus 2b plus c equals 9. And that would give us negative 2 times equation 2 is negative 2 times A is negative 2A, negative 2 times B, negative 2B, negative 2 times C, negative 2C, negative 2 times 4 is negative 8, plus 4A plus 2B plus C equals the 4A plus negative 2A is 2A, the B's cancel, negative 2C plus C is negative C, 9 minus 8 is 1. So now I have a new equation for 2A plus 2C equals 10, and equation 5 is new. 2A minus C equals 1. I could subtract those from each other to eliminate the A's. So 2A, I'm going to do that subtraction by changing it to adding the opposite. So we'd have equation 4 minus equation 5 is the same thing as equation 4 plus the opposite. So I'll change each of these three to their opposites. 2A, C, and 1 are negative 2A plus C minus 1. 2A minus 2A cancels each other out. 2C plus C is 3C. 10 minus 1 is 9. So I now have solved for C. It looks like C is equal to 9 divided by 3, or C is equal to 3. I could go to my equation 5, 2A minus C equals 1, and in place of C, put the 3, and then I could solve for A. So 2A would equal 1 plus 3, or 4, and then dividing by 2, that gives us A equals 2. So we have A and we have C. Now I can solve for B. So I could go to equation 2, A plus B plus C equals 4. In place of A, I'll put a 2. I'm solving for B. In place of C, I put a 3. So it looks like we have 5 plus B equals 4. Subtracting 5 from both sides, 4 minus 5 is negative 1. So B equals negative 1. Let's take those three variables, 2, negative 1, 3, and that's our solution. And this 2, negative 1, 3 can now go into our original function, y equals ax squared plus bx plus c. In place of a, I'll put the 2. In place of b, I'll put the negative 1. In place of c, I'll put the 3, and then I've got y equals 2x squared minus x plus, oh, looks like I left the plus off here, plus 3. And that's our function. We've answered the question, the quadratic function whose graph passes through these 3 points is given. Well, I hope that these 3 examples have helped you better understand the processes for working with a system of 3 equations. Don't hesitate to reach out to me if you need help with any of these types of examples.